Good morning, colleagues. The title of my talk today is Optoelectronic Optimization of Thin Film Solar Cells. Let me begin by thanking Juanjo Science for inviting me. I have known Juanjo from the time when he was at the Autonomous University of Madrid. I have visited Spain several times, Santander twice, and Bilbao, Madrid, and Potes once each. This is my first visit to San Sebastian. Such a lovely city. It's a coastal city. Will it be underwater in 2050? In 2100? Answers to those questions underlie my talk today. When a dyed-in-the-wool right-wing rag such as The Economist is concerned about climate emergency, it must be real, notwithstanding this blithering idiot. Just about 3 months ago, a major conference of scientists, engineers, and technology policy experts was held at Penn State. The aim was to review progress thus far and to outline steps to achieve drawdown. Drawdown is the point when greenhouse gas concentrations in the atmosphere begin to reduce. Energy generation is a major plank of actions to be undertaken for drawdown. Key point: the only form of energy to be generated and transmitted should be electricity. Next, at the point of use, convert electrical energy into other fuels if needed. Third, generate small amounts of electrical energy at the point of use. Fourth, use low pollution sources such as solar, wind, tidal, and geothermal. These sources represented less than 20% of global electricity generation in 2017, but a plausible scenario is that they can represent 90% in 2050. A focus of my research for the last decade has been ultra-thin solar cells. I am a computational electromagneticist, and therefore I undertake theoretical research. My collaborators, students, and I have recently achieved a bit of theoretical success, which I wish to share with you. The cost of generating solar energy has fallen dramatically in recent years. It is now cheaper to build and operate a solar park than a new coal-fired plant. In fact, the cost of generating 1 megawatt hour is between $60 and $142 with a new coal-fired plant, between $112 and $152 with a nuclear plant, and only $20 using solar photovoltaic panels. But solar farms connected to a grid are not enough. What we need is ubiquitous generation of electricity integrated with devices. Each microgenerator should run off solar radiation and or ambient light indoors. It should also be flexible and made of non-toxic, earth-abundant materials. Colored solar cells, perhaps less efficient somewhat, would also fill a niche. Today, CIGS and CDTE solar cells are the most common thin film solar cells. They have about 5% of the world market. CZTS, CZTSE, and gallium arsenide solar cells are also attractive, with gallium arsenide solar cells primarily for non-terrestrial use. But indium is not abundant, whereas cadmium and arsenic are toxic. The efficiencies of CIGS, CDTE, and the CZTS, CZTSE solar cells are not high. Certainly not high in comparison to the standard silicon solar cells used today in solar parks and on rooftops. So what we need to do is to increase the efficiencies of these thin film solar cells and at the same time reduce material use. These two objectives have guided the modeling research that has been undertaken by me and by Peter Monk at the University of Delaware. We work together. Now, a solar cell requires optical modeling as well as electrical modeling because it is an optical device as well as an electrical device. But optical modeling requires a solution of the wave equation, which is of the hyperbolic type. Electrical modeling involves a steady state diffusion equation and the Poisson equation, both of the elliptic type. Note that elliptic equations can be considered as parabolic equations at steady state. Optics modelers generally try to enhance the photon absorption rate, that is, the electron-hole pair generation rate in effect. But that is not enough because there is electron-hole pair recombination. Electrical modelers perform optical ray tracing or use the Lambert-Beer law, and thus they greatly trivialize optics. What is needed is an optoelectronic model with a rigorous photonic step and a rigorous electronic step, which is what Peter and I do. Let me now take you through the two steps for a CIGS solar cell. Right at the top of the solar cell is an anti-reflection coating made of magnesium fluoride. Below it is an optically transparent electrical contact layer made of aluminum doped zinc oxide. Below that is a buffer layer of intrinsic zinc oxide, which is put there to increase the open circuit voltage. Then there is a thin layer of N-type cadmium sulfide followed by a thick layer of P-type CIGS. This is where most of photonic absorption takes place. Then there is a passivation layer of aluminum oxide, and it is used to decrease recombination. And right at the bottom, there is a metallic grating. This is made of molybdenum. It serves as a reflector as well as a back contact. Now note that this reflector is a grating. That means it is periodic, and we take it to be periodic along the x-axis. We can also have it periodic along the y-axis, but that doesn't seem to help improve photonic absorption very much. We take sunlight to be normally incident. Light at all frequencies in the solar spectrum is taken to be an equal mixture of S and P polarized light in our model because direct sunlight is unpolarized. We have to determine the fields as functions of free space wavelength lambda naught. Now we use the rigorous coupled wave approach. In this approach, the optical relative permittivity is expanded as a Fourier series with respect to x. The reciprocal of the permittivity is also similarly expanded as a function of x. The Fourier coefficients of these two quantities, of these two expansions, are functions of z and the free space wavelength. The electric and magnetic field phasors are also expanded as Fourier series with respect to x, and the Fourier coefficients of these expansions are functions of z and lambda naught. All expansions are truncated, and as a result, we form 4 column vectors. The first column vector has permittivity, the second has the reciprocal of the permittivity, the third has components of the electric field phasor, and the fourth has components of the magnetic field phasor. We also make a diagonal matrix comprising the wave numbers along the x-axis. From the Fourier coefficients of a periodic function, we can construct a Toeplitz matrix. So we construct Toeplitz matrices of the optical relative permittivity as well as of its reciprocal. These are denoted by E and B. Now, Maxwell's kernel equations can be written as two systems of 2 by 2 matrix ordinary differential equations plus two algebraic equations. The solutions of the two algebraic equations are straightforward, and as a result, we get two matrix ODEs. Now we have a choice. We have four choices for the Toeplitz matrices M and N that have been identified here. We can choose M to be from the permittivity and N to be from the impermittivity. We can choose M to be the inverse of the impermittivity and N to be the impermittivity. We can choose M to be the permittivity and N to be the reciprocal of the permittivity. And then finally, the fourth choice is to have M as the reciprocal of the impermittivity and N as the reciprocal of the permittivity. How to choose? What we do is to assume that there is piecewise homogeneity along the z-axis, that is the thickness direction, that allows us to solve the differential equation in each piece very easily. Then we enforce the boundary conditions from across pieces and then find the reflection and transmission coefficients. And once we have done that, then we can find the electric field everywhere inside the solar cell. Now, for each of these choices, remember we have four choices. What we do is to determine the RMS error in the electric field relative to data from a rock-solid finite element calculation as the truncation parameter n sub t is increased. The error is averaged over the semiconductor layer only. The fastest reduction of the truncation error let us make the right choice for the S and P polarization states. For S polarization, it is choice 4, and for P polarization, it is choice 1. Notice that the choices are not the same for the RCWA converges reliably for S polarization, but much more slowly for P polarization. The electron-hole pair generation rate at any point can be calculated using the formula shown here. Maximum wavelength depends on the minimum band gap of the semiconductor. Minimum wavelength is 350 nanometers. S is the incident power spectrum, which we take as 1.5 AM global standard. The output of the photonic step is a 2D electron-hole pair generation rate. Now, a voltage is applied along the z-axis, so the DC current will be primarily directed along the z-axis. Also, the period along the x-axis is minuscule electrostatically. So we create a 1D electron-hole pair generation rate in which we have averaged over x. This becomes the input to the electronic step in which equations are solved arising from a 1D drift diffusion model. Here, Q sub E is the elementary charge, R is the electron-hole pair recombination rate, N sub F is the number density of trapped charges, P is the number density of holes, N is the number density of electrons. Epsilon dc is the quasi-static relative permittivity, phi is the scalar potential, J sub n is the electron current density, J sub p is the hole current density. All of these quantities are functions of z, for the simple reason that the semiconductor layers are assumed to have z-dependent band gap. Our model is currently configured to incorporate three nonlinear mechanisms of electron-hole recombination: Shockley-Reed-Hall, Auger, and radiative. By definition, the current densities involve the electron mobility mu sub n and the hole mobility mu sub p. as well as the quasi-Fermi potentials E sub Fn and E sub Fp, in which V sub Th is the thermal voltage. N sub C is the density of states in the conduction band. N sub V is the density of states in the valence band. E sub C is the conduction band energy. E sub V is the valence band energy, and their difference is the band gap. Crucially, in this model, we let the band gap be dependent on Z. This dependence of the band gap on Z can be engineered when the solar cell is made by changing the chemical composition of the semiconductor. In the Boltzmann approximation, the quasi-Fermi potentials are assumed to be far away from the band edges. Accordingly, the charge densities can be written down in terms of the intrinsic energy level E sub I and the intrinsic carrier density bar N. The electron affinity chi depends on the semiconductor and the band gap, and E sub O is an arbitrary reference energy, which is a constant needed in electrostatics. So, the Boltzmann approximation simplifies the current densities in terms of the gradients of the two charge densities, the scalar potential, and the built-in potential for electrons and for holes. Here, N sub 0 is an arbitrary constant corresponding to E sub O. In the vicinity of the contacts, the semiconductor is modeled to be in local quasi-thermal equilibrium, as the contacts are assumed to be ideally ohmic. Then, Dirichlet boundary conditions can be used for the charge densities and the scalar potential. Next, various quantities are non-dimensionalized. The result is that we have three systems of equations that are similar to each other. Since they are all of the same kind, they can be combined into a single system of equations, and these have to be, of course, solved. We used the hybrid discrete Galerkin formulation with fifth-degree interpolating polynomials and an adaptive mesh to determine the total current density as a function of the voltage Vx applied to the terminals of the solar cell. We can then compute the power density, the maximum power density, and the efficiency. Our objective is to maximize efficiency in relation to the geometric parameters and the band gap variation in the semiconductor layer. We used the differential evolution algorithm for this purpose. It's available on MATLAB, etc., and so I will not dwell on it here. Let me close by showing you a few results. First, for a CIGS solar cell. The proportion of indium to gallium can be varied by changing the parameter xi from 0 to 1. Hence, the real and imaginary parts of the optical permittivity of CIGS can be changed. The electrical properties of CIGS also depend on the gallium proportion xi. The electrical properties of intrinsic zinc oxide and cadmium sulfide are known, as also the optical relative permittivities of all other materials involved in the solar cell. The model was validated against experiments with homogeneous CIGS layers and provided comparable results. For xi equal to 0, 15.05% versus 15%. For xi is equal to 0.75, 18.12% versus 19.5%. And for xi equal to 1, 9.92% versus 10.2%. The best experimental result is 22.6%, but we did not have all the parameters needed to attempt a decent validation. But note the best experimental efficiency of 22.6%. This is for 2200 nanometer thick CIGS layer with a homogeneous bandgap. We then decided to turn to sinusoidally graded bandgap for the CIGS layer. Our model indicates that a 600 nanometer thick CIGS layer with a sinusoidally graded bandgap can deliver the same efficiency as a 2200 nanometer thick homogeneous CIGS layer. This is important because indium is not abundant on Earth. If we stay with a 2200 nanometer thickness, sinusoidal grading increases the efficiency to 27.7%, which is a relative increase of about 30%. The optimal bandgap is not complicated. It is mostly flat, it is high towards a CDS layer, and there is a triangular profile in the middle of the CIGS layer. Large parts of the CIGS layer have minimum bandgap. These regions have high generation rate because less energy is needed to excite a charge carrier from the valence band to the conduction band when the bandgap is smaller. Near the CDS layer, the bandgap rises quickly. This increases the open circuit voltage. Let me move to another promising solar cell in which CZT SSE is used as a semiconductor material. The proportion of sulfur to selenium can be varied by changing the parameter Xi from 0 to 1. In other respects, the CZT SSE solar cell is similar to the CIGS solar cell. The best experimental efficiency is 12.6% with a 2000 nanometer thick CZT SSE layer with homogeneous bandgap. This does not compare favorably with CIGS, which has 22.6% efficiency. But CIGS contains a rare indium, whereas CZT SSE contains earth-abundant materials. We need to increase its efficiency. With sinusoidal grading of the bandgap, our model predicts 19.6% efficiency, close to CIGS. But wait, reduce the thickness by 60% to 870 nanometers, and the model predicts the optimal efficiency of 21.7%. Half the material, twice the efficiency. Who could want anything better? The optimal bandgap is again not complicated, mostly flat, high towards both faces, and one triangular profile in the middle of the CZT SSE layer. So in summary, I have presented to you a detailed and rigorous optoelectronic model. The photonic step is 2D, but increased to 3D is straightforward and has already been done by us. The electronic step is 1D, which is satisfactory because a voltage is applied across the solar cell. We have found that the optimal bandgap grading can increase the efficiency by 25% and more. As I had mentioned earlier, my main partner in crime has been Peter Monk from the University of Delaware, also Tom Anderson and Faiz Ahmed, who are postdocs and a student respectively. This work is being funded by the US National Foundation. Torben Lenau at the Technical University of Denmark and I have begun to work on colored solar cells, but that's a story for another day. Thank you, colleagues, for listening to me. Thank you. I am here today somewhat in an evangelical role. The earth, the air, the land, and the water are not an inheritance from our forefathers, but on loan from our children, said Mahatma Gandhi more than 70 years ago. I have told you today of my efforts during the last 10 years or so as a small contribution towards that goal. In the next few minutes or so, I would like very much for you to tell me what kind of efforts you can make as scientists towards that goal.